All right, so in this video, we're going to be now talking about the second style of dimensioning, which is called broken chain dimensions. So what it does is it combines the chain dimensions that we've looked at, which is another style of dimensioning, and it adds an overarching control on it, okay? So broken chain dimension, what I've done is I've kept the same part, same tolerance, all that stuff. I erased off the reference dimension from the chain dimension video. And now what we're going to do is we're going to let this area right here become the runout. So we're going to have, and in this case, this will now be a controlling dimension, 5.000. Okay? So the 5.000, this one was a 3-place decimal. We'll put this one at a 3-place decimal so you can see some of the differences here. Okay? So now instead of it being a reference dimension, this is an actual dimension. This dimension is now controlled by the unspecified tolerance block. Because it's 3-place decimals, that means that this 3-place decimal is plus or minus 5/1000 of an inch. So in this particular case, we still have these first four the same. We have this overall dimension here, and I'll put on there plus or minus 5/1000 so you can see it. And then we have to ask ourselves, well, what is this? Okay? So a couple of things here. In the previous one, when we looked at just the chain dimension, we saw the maximum could be 5.040, the minimum could be 4.960. So 40 thousandths above, 40 thousandths below, that's the overall length of the part. In this particular case, the overall length of the part is controlled by this dimension. So the max length would obviously be 5 plus the 5/1000ths, which would be 5.005. And the min length would be 5 minus 5/1000ths, which would be 4.995. In this scenario, this top or main overarching dimension is controlled by the tolerance, and so you have a lot tighter tolerance control with the overall length of the part. We now have where this question mark is what we call a runout. Okay, so in this area, this is where all the accumulated tolerances run out. This is now where it becomes the wiggle room. So in the chain dimension style, every one of these, added up or subtracted, and so your runout was at the very end, total length of the part. This case, this now becomes the runout because the total length of the part is dictated by another dimension. So if we were to look up or calculate up how this is calculated, we would do it the same way, okay? So in this case, we want to see what is the maximum of this area with the question mark, and what is the minimum with this area with the question mark. So as you think through that process, here's the secret. If we want to look at the maximum, we want to push this edge out that way, and we want to push this edge as far back this way as we can go, okay? So let me just draw these arrows on the inside here. We want to push this edge back, which means this is going to be minus, 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 to make this go as far back this way as we can. And this arrow here pushing this edge that way, we want that to be the plus, okay? So in this particular case, if we want to see the maximum of that area, so here's how we calculate that. We want to take this edge, and we want to move it that way. So that's going to be 5 plus the 5/1000ths to move it out as far as we can go, which would be 5.005. So that's the maximum this edge can go over. Now we need to take the edge this way, and the shortest it's going to go. So now we're going to use the minuses of all of these. So 1 at 3-place decimal would be the 1 minus 5/1000ths, which would be 0.995. We would have the 1 minus 0.01, which would be 990. The next one, 990. And then the next one, 990. And all I'm doing there is I'm just simply taking out the tolerances there to make this edge as short as possible, this next one as short as possible, this next one as short as possible, this next one as short as possible. That allows all of these to move over this way as far as possible. In this particular case, we subtract out the maximum on that side, the minimum on that side, and what are we left with here? Let's see here. So this is going to be a 1 point, so there's 1, 2, 3, what is that, 4? 0, 4, In this case, this is the maximum that part can be. We're going to do the same for the minimum now. We're going to take this edge and move it as far in as we can, and we're going to take this edge here and move it as far that way as we can. So we're going to take this process and we're just going to flip it. So instead of the 5.005 to move that out as far as you can go, now it's going to come in as far as you can go. So the 5 minus 5 thousandths is 4.995. And now each one of these maxed out. So 1 plus 5 thousandth is 1.005, 1.010, 1.010, 1.010. So if we were to subtract all of these out here, we would have 0, 1, 2, 3, 4, 96. Okay, so 0.960. So this runout area is as small as it can be at 0.960. It's as big as it can be at 1.04. And that allows us to be able to calculate up this tolerance. Now, if we were to look at the tolerance range of this part, we subtract out the max minus the minimum, 1.040 minus 0.960, okay, we still get the 0.80. That was the same tolerance range that we looked at with the chain dimensioning. So why is it the same tolerance range? Well, the reason is our tolerance decimal places have not changed. So it was still a 3-place at each end. Okay, so in this case it was 3-place here. In the chain dimension examples, this had a 3-place. Instead, for this broken chain, I just simply used the top one as a 3-place. Okay, so the tolerance accumulation is still going to be the same. The difference here in the scenario, though, is that in the chain dimension, your overall part length had that 80 thousandths play. Okay, so 0.08 play in the overall length. In this case, the overall length is still controlled by that dimension, but the runout, or that wiggle room, the maximum amount of wiggle room, that 80 thousandths for that tolerance range, is in that gap right there. So that's the runout area. So that's the second way that engineers and designers will dimension parts. This is a very common way to dimension parts. In fact, this is one of the more popular ways depending on which industry you're in. The reason for that is because a lot of people like to know the overall dimension, sometimes with as far as ordering stock material, and they can use that for reference dimensions too. But if you have parts that are mating, so if this plate was laying into, let's say, another part, those types of things, sometimes engineers and designers will want limit controls on those parts or the outside controls. And so it just has a tighter overall control, but the tolerance is still here in the runout area. Okay, so in this particular case here, this is a common way. Typically, if you're in my lower level drafting and CAD courses, this is typically how we will design parts. So you know the overall length of it, and then you know the individual lengths. Remember, again, you never, for machine or mechanical design, you never put all of your dimensions in here and put a guiding dimension up here. The reason for that is because if you have a dimension in here and you add up all the tolerances of all 5 of these dimensions, they will err with your dimension and tolerance for your overall dimension. Okay, so that overall length dimension, that's why you never add in that last dimension for machine or mechanical design. Now in architecture, it's different. In architecture, you'll have one row of dimensions that'll go to walls, and one row of dimensions that'll go to windows and doors, and one row of dimensions that'll be overall, and they're all dimensioning the same stuff, and it does not have the runout area, but that's architectural design. It's a different style, a different field of design work. For machine or mechanical design, where we have part accumulation of tolerances, the tolerances are what dictate if you have an overall length or if you have just straight chain dimensions. So that's another way to dimension a part.